Alrighty, hello class. Um, I'm about 20 minutes early today. That's because I finished my other lessons early, so I thought I would just get rolling with this one and not waste any time. Um, so I hope you're all doing well. I'm going to do a little change of plans today because I was checking out the College Board website, and on that website I saw that they had released some questions that are sample questions specifically for the 2020 exam. So we're going to take a look at these sample questions today, and these are going to cover, or this is going to be basically what your actual AP exam is going to be like, okay? So let's dive right in and see what this. I haven't looked at these questions yet, so I have no clue. All right, so question one, which is supposed to take 25 minutes. So the whole exam is only 45 minutes. You got a 25-minute question and you got a 15-minute question. So it says a small sphere of mass m is suspended by a string of length L. The sphere is made to move in a horizontal circle of radius r at a constant speed as shown above. The center of the circle is labeled point C, and the string makes an angle theta naught with the vertical. Two students are discussing the motion of the sphere and make the following statements. Student 1 says, none of the forces exerted on the sphere are in the direction of point C, the center of the circle path. Therefore, I don't see how there can be a centripetal force exerted on the sphere to make it move in a circle. Okay. Let me pick apart student 1's argument just before we, because when I see the problem, I'm just like automatically thinking about how are you going to analyze this problem in terms of physics, okay? And if I wanted to think about this from a side view, what if we had a side view of this problem and I do a free body diagram? Well, we're going to have the tension. The force of tension is going up like that, okay? And then we're going to have it's moving around in a circle like this, back and forth. So the center of the circle is like right here, roughly, okay? Now it's that way, directly towards the center of the circle, okay? So student 1 does not know what they're talking about. Student 2, I see another problem. The tension force exerted by the string is at an angle from the vertical. Therefore, its vertical component must be less than the weight mg of the sphere. That means the net force on the sphere has a downward vertical component, and the sphere should move downward as well as moving around in the circle. Okay, so for part A, it says, what is one aspect of student 1's reasoning that is incorrect? Explain why. So what I would say is that while none of the individual forces point to the center, the net force does. Okay? So the centripetal force is basically the net force. Okay? So that's what I would say. For part B, it says, what is one aspect of student 2's reasoning that is incorrect? So the tension force is at an angle from the vertical. But if we think about it, do you see how it's moving in a horizontal circle? The sphere is moving in a horizontal circle. it's not moving vertically. Okay, so they kind of answered their own question. The vertical component must be equal to the weight mg of the sphere. So the vertical component of the tension is actually equal to mg. It's not less than. Okay? So there is no net downward force. That's what allows the sphere to move in a horizontal circle. Okay? So student 3 correctly derives the equations F net equals tension times R over L and mg equals blah. Explain how one of these equations can be used to challenge student 1's claim. All right. What was student 1's claim again? Explain how one of the equations can be used to challenge student 1's claim. So what I would notice here is that let me annotate here. Okay, so we've got basically a right triangle that's formed right here. And this part of the triangle is R. Okay? So if we look at R over L, R over L is equal to, that's basically opposite over hypotenuse, so it's equal to sine of theta, which is going to be, now if we look at our tension, so if this is our tension pointing up, let me delete that. If this is our tension pointing up, okay, then basically sine theta is going to give us the horizontal part of the tension. That's the x component of the tension. That's T sub x, okay? So basically, I would use the equation F net equals F sub T times R over L, which is the horizontal part of the tension. So we can see that the net force is in the horizontal direction. The net force is in the horizontal direction. Towards the center of the circle. Okay? So that's how I would challenge it. Okay. Explain how one of the equations can be used to challenge student 2's claim. So student 2's claim is that the tension exerted by the string, the vertical component of the tension, must be less than the weight force mg of the sphere. Okay, so if we, let's go back to the Pythagorean Theorem. Okay. All right. So basically, by the Pythagorean Theorem, this height right here is L squared. Triangle, we have L squared equals R squared plus Y squared. Okay. I'm going to move this so you guys can see it. All right. So that means that Y equals L squared minus R squared to the 1/2 power. So basically what that means is that the vertical leg of this triangle is L squared minus R squared to the 1/2 power. So if I wanted to know what is cosine of theta, cosine is adjacent over hypotenuse, so it would be L squared minus R squared to the 1/2 over the hypotenuse, which is L. So that's equal to cosine theta. So what happens if we take the tension and we multiply it by the cosine of theta? That's going to give us the vertical portion of the tension. So basically what I would say is that this is actually equal to F sub t cosine of theta, which is equal to the x component of the tension. Or sorry, the y component of the tension. So what I would say is the second equation says that the tension, the y component of the tension, is equal to mg. So that definitely challenges student 2's claim, because student 2 says that the vertical component of the tension is less than the weight. But we just showed, or equation 2 says that the vertical component of the tension is equal to the weight. All right. Students observed that the radius r increases as the speed of the sphere. Together they derived the equation r equals v times square root of L over g to calculate the radius of the sphere. Sebastian says my paper is overexposed. Let me do that. And Sebastian says my paper is overexposed. So here, let me put some clothes on my paper. There. I'll put some swim trunks on so it's a little bit more modest. Okay, I don't want to overexpose my paper. All right, students observed that the radius r increases as the speed of the sphere. Regardless of whether this equation is correct or incorrect, does it plausibly model the student's observation about the relationship between r and v? Why or why not? Okay, I don't want to overexpose it, so I'll partially expose the piece of paper like that. So what I would say is we can see that this equation shows a linear relationship between r and v. So as v goes up, r goes up. So I would say it's consistent. Okay. This equation does not correctly model the relationship between r and v if v is very fast. Explain why. Basically, that equation shows that r can increase without limit. Right? It's like you make V faster, you make R bigger, always. So for basically what that equation says is that, R can be as large as we want it to be. However, the maximum value that R can take is equal to the length of the string, right? If we whip this thing around really fast, it's going to go basically horizontal. So the radius can't be bigger than L. So that equation can't be right. Wow, this question just keeps going. Holy cow. This, I have to say, this exam seems much longer than the AP Physics C exam that I did. This is a really long exam. So instead of moving in a horizontal circle, the sphere now moves in the vertical plane, so it's a simple pendulum. The maximum angle that the string makes from the vertical can be assumed to be small. The graph below shows the data for the pendulum period as a function, square of the pendulum period, square of the, whoa, I can rotate it. Whoa, whoa, that's pretty cool. Whoa, whoa. Square of the pendulum period as a function of string length. Okay, so for part G, we've got the equation that period equals 2 pi square root of L over G. All right, so we square this equation, we get period squared equals 4 pi squared over G times L. Okay, so the slope, basically we can see that the slope of this line is 4 pi squared over G. Okay, so explain how the graph would change under each of the following circumstances. The mass of the sphere is increased. Does the slope depend on mass? No. Okay, so I would say there's no change for G. H, what if the maximum angle is decreased? Do you see, does angle have any effect on the slope? No. So I would say no change. All right. However, what if the pendulum is taken to the moon? The moon has gravity goes down, which would mean the slope would go up. So I would say steeper slope. All right. All right, part J says the graph above shows the angle theta. Jin K asks, so the exam is 2 very long questions. This is a sample exam, so I would say the answer to that question is yes. It's going to be 2 long questions. The graph above shows the angle theta from the vertical as a function of time. Explain how this graph shows evidence of a net force acting on the sphere, and how it shows that this net force is a restoring force. So I would say that the graph is bendy. The graph being bendy implies that there's an acceleration, and acceleration implies that there's a net force according to net force equals ma. So there's definitely evidence for a net force acting on the sphere through that chain of reasoning. Why do I say that the net force is a restoring force? Basically, we can see that the angle, or I would say, notice how when the string angle is negative, that the acceleration, this graph is bendy up. So I would say when theta is less than 0, the acceleration is greater than 0. It's bendy up. When the angle is positive, it's bendy down. So basically the acceleration and the angle are always in opposite directions. So that means that there's something that's trying to get you back to theta equals 0. Okay? Below indicate the direction that the sphere rotates as it is swinging. In order for the sphere's rotation to change direction, a torque must be exerted on the sphere. When the sphere is at its maximum rightward displacement, what is the direction of the torque exerted on the sphere with respect to the point of attachment between the sphere and the string? Briefly state why the torque is in the direction you indicated. Okay. So what we can see, so it's saying what is the direction of the torque on the sphere right here at this location. So right at that location, we can look at it. It's right at this location. It was swinging to the right. Okay. So basically, as it was swinging to the right, I'm going to draw a graph of omega versus time. Okay? And let's suppose that this is the time at which it reaches its maximum rightward swing. So as it was swinging to the right, we can see that the angular velocity is in the counterclockwise direction. Okay? So we start out with a positive angular velocity. Okay? Now, once it starts swinging to the left, it's now going to be swinging in the opposite direction. So once it swings to the left, now the rotation is going to be against that in this direction. Okay? So the angular velocity ends up negative. All right? So we have an omega versus time graph that looks like this, where that is the point at which, okay? So basically we can see that omega goes from positive to negative. So that means that we have a negative angular acceleration. And then according to net torque equals I alpha, we can see that the net torque must also be less than 0. Okay? So that's what I would say. All right, we're finally on to question 2. A spring with an unstretched length L is hung vertically with the top end fixed in place as shown above. A block of mass M is attached to the bottom of the spring as shown in figure 2. And the spring has a length L2 greater than L1 when the block hangs at rest. So basically X, the extension, is L2 minus L1. Okay? When the block is then pulled downward and held in place so that the stretched spring has a length L3. So what that means is that basically the amplitude of the simple harmonic motion is L3 minus L2. right? Because it's the distance, the amplitude is the distance beyond the equilibrium length. So we have x and we have amplitude based on this information. The student releases the block. Consider the time during which the block is moving upward towards its equilibrium position and the spring length is still longer than L2. Indicate whether the total mechanical energy is increasing, decreasing, or constant for each of the systems listed below and explain why. So this is a good one because it talks about definition of the system. What if the system is only the block? Now we talked about if the system is only the block, there's no gravitational potential energy, because in order to have gravitational potential energy, we had better have in order to have, oh my gosh, I'm losing it right here. In order to have gravitational potential energy, the system has to be block and Earth. Okay? Okay. In order to have elastic potential energy, the system has to include the spring. So because system 1 doesn't have the Earth or the spring, we don't include elastic potential energy and we don't include gravitational potential energy. So the mechanical energy of system 1 is just kinetic energy. All right? So if we look at it, it's actually going to accelerate upward from L3 towards L2. So the velocity is increasing. All right? So I would say that the mechanical energy of system 1 is increasing. For part B, it's a what if we consider the block and the spring? So if we consider the block and the spring, then the mechanical energy is both kinetic and elastic potential. Okay? So what's happening, and then we have an external force, which is gravity. So in system 1, the external forces are gravity and elastic. But in system 2, we're including the spring in the system, so an external force is gravity, only gravity. Okay? So if we think about system 2, we have a downward external force from gravity, whereas the displacement is upward, right? Because it's moving up back towards the equilibrium position. So what that means is that the work done by the external force is negative, because the formula for work is F displacement times cosine of theta. And so the angle between them is 180 degrees. So because the external force is doing negative work, that means that the external force is a joule thief. It is a joule thief. Gosh darn it. The system 3 consists of the block and the Earth. So our energy is going to be kinetic plus gravitational potential. We can see that it's going upward, so the y value is going up. The y value is going up. Also, it's accelerating upward, so the speed is going up. So both of these terms are going up. Okay? So that means that the mechanical energy of system 3 has to be increasing. So I think the trickiest one here is B, because this one is tricky because we have that the speed is going up, but that the extension of the rubber band is going down. So it's kind of like which one is bigger. It could go either way. Now, of course, if the system was the block, the spring, and the earth, the mechanical energy would be constant. All right. D, the block is released at time 0. The length of the spring is shown in the graph above as a function of time, during which intervals, if any, is the weight force acting on the block greater than the spring force acting on the block. Explain your reasoning. Well, if the spring is at length 2, okay, if the spring is at length 2, then we know that that's the equilibrium position. It says that figure 2 is the equilibrium position. So at equilibrium, we have, so right at that spot right there, right at that spot, we have, that's an equilibrium position. So we're going to have Kx equals mg. So we have Kx equals mg right there. Okay? Actually, I think I'm going to, so Kx equals mg right there. And also, we're going to have Kx equals mg right here. So those are the 2 points where Kx equals mg. All right. If we look at L3, the rubber band is more extended. Okay? So if we have more extension, the weight force stays constant. So for this interval right here, we have more extension. So we're going to have more Kx than mg. All right? So basically for that interval right there, we have Kx greater than mg. Okay? For this interval right here, we have less extension of the rubber band. So we're going to have, in that interval, we're going to have mg is greater than Kx. Okay? And then here we have, in this interval of time, we have more extension. So we're going to have, once again, Kx is greater than mg. All right. Part E says the block reaches its lowest point after oscillating several times. The student attaches a new block of mass little m greater than big M to the block of mass big M without exerting any noticeable force on the block of mass big M or changing the energy stored in the spring at that instant. In a clear, coherent paragraph-length response that may reference equations, explain how the graph of length versus time will change and why. So, what we would do, so I'm going to draw the other graph. Okay. So first of all, we're going to have the equation t equals 2 pi square root of m over k. So we increased the mass of the system. So that means that the period had to go up. Okay? So I would say thus the period increases. The equilibrium length of the system okay, so I'd say period increases since the mass went up. Okay? Also, since the mass increased, L2 has to be bigger. So why would I say that L2 has to be larger? It's because at the equilibrium length, that basically we at equilibrium we have kx equals mg. So if we increase the mass, we have to increase the extension. So L2 is going to be bigger. So how is the graph going to compare? Basically, L2 is going to be larger, so L2 might be up here instead. Okay, and instead we're going to oscillate about that length. So it's going to look something like this. All right. So the amplitude is going to be smaller, and it's going to be oscillating about a different point. The period is going to be longer. All right, so I think that's it. That's the entire exam. So that was interesting. One of the things I noticed is that and this is kind of what I predicted. Notice how all of the questions were about writing. Why would they do that? It's because you're not taking the exam on a piece of paper, you're taking it on a computer. And it's really hard to do equations on a computer, and because it's all about typesetting. So it looks like they're not going to ask you to write equations. They're going to ask you to explain everything in paragraphs. So the amount of math on the test is going to be quite small. So what I would recommend doing is have a scratch piece of paper, work out the math on a scratch piece of paper, and then translate the math into words for your actual response. Okay? I think that's the way that it's gonna be. So I actually think that I wouldn't do well in this format of exam because I like to write equations. That's sort of my way of understanding things, as opposed to writing paragraphs. So thanks for watching. I hope that was helpful. I'll be posting more about the actual AP exam in the coming days. And we'll have any questions you have, I'll be on Discord for a longer amount of time on Wednesday of next week because your AP exam is Thursday. So have a great afternoon, and I will talk to you tomorrow.